All right, so here's the second half of chapter 5.1. We're talking about turning points here. So when we're considering a turning point, we're always considering x marching along from left to right. So as our x values march along left to right, our y values are decreasing. So as we go from left to right on the x, the y values are going down. Just imagine like a little Etch-a-Sketch. We're rotating the knob to go down here until we get to this point. Now, as we march along with our x's, our y values are increasing. So that change from y's decreasing to y's increasing is called a turning point. That's this point right here when it turns. So let's consider some common functions. Now I'm actually going to put those in quotes because these aren't the parent functions that I'm going to graph here. They're just like a generic kind of whatever graph. So some linear function has 0 turning points. So this one has 0 turning points. It's just a straight line. There are no turns. Quadratic is going to look like this, basically. And that has 1 turning point. A cubic, now the parent function is just going to look like this, so it doesn't really look like it has any turning points. But a generic one, if you had a couple more terms there, would look like this. So there are 1, 2 turning points. A sort of generic fourth degree is going to have an end behavior of infinity to the left, up, down, up, and infinity to the right. That's 1, 2, 3 possible turning points. So it could have 0 turning point, or it could have 1 turning point, or it could have 3. If we look at x to the 5th, maybe you're noticing a pattern here. 3 turning points there. Starts at negative infinity. Up, down, up. Yep. There we go. So now that has at most, and x to the 5th is going to have at the most 1, 2, 3, 4 turning points. So the take-home idea is that the number of turning points is going to be 1 less than the degree of the polynomial. Or the maximum number of turning points is going to be 1 less than the degree of the polynomial.